get back on schedule. Yeah. Let's see if we can do it. It's not like a publication. Okay, so in this session we'll have once again speakers who don't need an introduction, but I'll give a short one. I'll give a short one anyway.
Do not deserve an introduction.
So Yishay Mansour, in addition to being an amazing learning theorist, is also a very frequent collaborator with Aviv. I think over 30 papers or something they have together, and he has algorithms named after him on low-degree polynomial learning. And yeah, I'm excited to hear his talk.
Thank you very much. Okay, so the subject will be sort of about type 1, type 2 errors. We'll get into this, but there is more things that we need to start. So first of all, this is today's real birthday of Aviv. Sort of, for those of you who missed, it's sort of like the unlikely likelihood that we chose the week that includes the true birthday. So happy birthday, Aviv. I didn't put the number because no need to know. Okay, so I was amazed how few pictures I have of Avrim and myself. This is sort of in a cult in Amsterdam. I have no idea what's the background here. And this is sort of in Chicago with Nicolo when we were together. But the few photos sort of do not cover the very many joint works. So notice that there is like a gap in the... I started at 1990, but we were together 3-4 years before in MIT. Somehow we got a lot to talk together, both with Avrim and with Rob, but we never sort of wrote anything together until the three of us left MIT, went to our ways, and then we can work together easily. And sort of you can see that over the year we had many joint papers and many joint researchers. It did start sort of in MIT. Hopefully this is the right building. I know that the LCS is not anymore in this building, Ron, right? And okay, I have also my advisor here to check on me. Okay, so we were together sort of in 87 to 90. I think Avram, you were sort of one year after us, 87 to 89. And this is sort of Ron from your first class. And I had all the class notes, but I suddenly moved in office and had to throw a lot of things away. But I did keep this. This is the first machine learning class. And I think it was mentioned, but I want to thank Ron to introducing us to this, and mainly sort of to getting us excited. And I think it's also shaped the field because, like, you can see here, okay, so this is Ron, Avrim, Mike Kearns, Rob, myself, Sally, and Bob Sloan. They were all PC chairs of code. They were all in the same class. So this is sort of how influential this class was in the later year, in the shaping and in the growing of machine learning theory. Okay, so it's always tricky to find a topic to talk about in those birthday workshops, etc. But in retrospect, I always am able to explain why did I choose this paper, except that I had the slides, and I have my two co-authors here, to answer any really tough questions that you might have. But here is my sort of wishful thinking. So Liz was my student, Han is sort of Avrim's students, and also Lee was in TTI and worked together with Avrim. So I do have an excuse why did I choose this paper. Okay, so let's start sort of from Machine Learning 101. This is sort of, we did talk about the class. So in the PAC model, the basic paradigm is that you have an unknown distribution, you see a sample, and you want to select a classifier. And usually the error rate is like classification node. It's a 0-1 loss. And the PAC model would like us to assume sort of that with high probability, we can select a classifier from the class that you're looking at that would have a low error. This is like the realizability assumption that we like to make. And the basic thing is sort of what is the sample complexity size. So I guess under realizability, probably just on 1 over epsilon is enough, but for the agnostic case is 1 over epsilon squared. So this is sort of the basic thing that you would like to sort of address. And the main part of the theory is really talking about training versus test. How do those, what you see on the sample is reflected in the population that you would like to estimate? And this sort of sample size in the PAC model is really saying to you, okay, you can, what you see is what you get. What you'll see on the sample is what you'll get later when you deploy it to the population. Okay, and we do have also sort of, okay, so here I get the sample size for a finite hypothesis class. Of course, there's many works on infinite hypothesis class, VC dimensions, etc. Okay, but in some sense, okay, if I want to summarize the talk in one sense, not all errors are created equal. And here's sort of two error types that you can think of. False positive rate and false negative rate. I'm usually amazed how many times I can get them wrong, but hopefully false positives, meaning that you're predicting positively and you're incorrect. False negative, you're predicting negatively and you're incorrect. So if you look at this picture, like you're predicting positively in this region, but your C part is sort of your B part is your incorrect part. And when you're predicting negatively, you have another type of an error. And the question of balancing those two errors, okay, one way to balance them is just sum them up. Okay, then you get the usual classification error. But in many applications, this is not really what you want to do. Okay. So let's start to think about a more complex setting. So the complex setting that I'll have here in mind is more complex than this. Think about searching for books in a library. Okay, so there are no more any libraries, there are no more any books, but science fiction is what Ron told us about. So this is like a science fiction idea. So when you look at the book, so this is like a set of good replies. So information retrieval, which originated with librarian, they really thought about like a query and a reply. And the question, how do you evaluate a reply? So a reply is usually not like a book, but sort of a set of things. So the prediction is really sets, and you want to compare sets. So going back 1961, this is 1 year after I was born and a few years before Avram was born, Cyril Clevendon, so he's Britannian computer scientist, he sort of gave us sort of one tool to address it, and this is a tool that he's sort of using today. Prediction and recall, sort of you want to balance two different things. So the model is like there's a true set and there's a set that we are returning. We want them to be identical, but we don't want a 0-1 loss that says it's the same set. So really we are looking at two different things. So prediction rate is in some sense, we are looking at the intersection compared to the item that we return. Sort of how many of the items that we returned are really interesting. The recall rate is the other way around, right? How many of the true items are we returning? So, okay, so those also, they are basic ideas. This is called also this false discovery rate, sensitivity, power, because they are measuring things that we are interested in, right? Sort of on one hand side, we want our answers to reflect the truth. On the other hand side, we want to capture everything that needs to be captured. Okay, so this is sort of the 60s point of view. So, okay, so let me sort of slightly define more precisely what do I mean by precision and recall. We will, so think about this like a recommendation to the user. So the user has some set of items that he is interested in. We give it, so this set is the black arrows. We give it a subset, which are the V's. Those are the sets that we think that the user would like. So what is the precision? So we look at items that are both recommended and the user likes, compared to the number of items we recommended. The recall is the other way around. We look at the items that the user likes and we recommended compared to the total number of items the user liked. If I want to connect it sort of to a more sort of machine learning system, you can think about it think of it, you have like a multi-class, you have like say a picture and you want to predict a few things, a pen, a window, a fridge, a desk. This is sort of what's in the picture. And really sort of you can think that what we are trying to do is given a picture, we are trying to sort of guess the labels here. And we are going to be measured by how many of the correct label we put in and how many of the labels that we put in are correct. So the model that I'm going to talk about is sort of a one-sided model, and I think it fits many of the applications. Definitely recommendation system, but also many other applications. So in test time, we want to provide an accurate list of recommendation. But what do we see in training? In training, we usually see only the positive examples. Sort of, we see, okay, this is a typical user becoming a robot. And what we will see is sort of that this user likes this item. Right? So we'll never observe like the negative example. We'll never sort of observe the things that the user doesn't like. And we're not going to observe at any point all the things that they like. Right? So we are just going to get a sample, a single item that the user like. Okay, so now we need to give a precise model. So we have a set of, okay, a set of, think about it as a bipartite graph. So we have a set of nodes on the one side, and this is sort of the set of items. And our hypotheses are sort of mapping between them. So those are the different users, those are the different items, and the hypothesis is for each user gives a subset. So there is an unknown graph, a mapping from users to subsets. We have a distribution over the users. And what we see in the training time, we see sequences of a user and an item that they like. Okay? All right. So basically, we are seeing xi and vi, and xi is like a random user, and the vi is chosen uniformly from sort of a subset that the user is interested in. So first of all, anyone who knows precision recalls know it, but just let's make sure that everyone is with me on this. You can achieve either one trivially, right? So you can achieve perfect precision or perfect recalls easily. You can either output an empty graph or you can output the complete graph. Both are useless. Let's just put things on the table. They are useless, but they are in some sense like sort of the benchmark. Right? So this is what you would like to get much better than. So what would be our learning objective? Okay, so our learning objective now, okay, so since we can get each one of them perfectly individually, we want to combine them in some way. So the way that we selected to combine them, which is fairly standard, is sort of look at the average thing. So average the precision loss and the recall loss, and you would like to minimize those. And later we'll sort of look sort of that our goal is sort of to find a mechanism or an algorithm that would guarantee us, ideally it would be comparing to the best model that we have, but sometimes we'll need to suffer sort of a multiplicative loss. When we'll get to it, we'll see. I'll claim the Y. This is not the only way of sort of combining precision and recall. Another popular one is called the F1 score. You see, you multiply the precision and recall. So if one of them is 0, you're going to get a 0. This is a different way of combining them, just for the background. What we really would like to sort of is to have a training size that does not depend on the number of nodes or edges. Right, so number of nodes is the number of users, the number of edges sort of is how much items are liked. So I would like my training size to scale only with the relevant parameters. Okay, so what are the challenges? So first of all, the ERM oracle is useless here, right? Because you don't need to give it any input. Regardless of what you saw, the complete graph is always consistent. Okay. So if we want to get a learning, we need to do something else. The other more tricky thing is that you cannot get an unbiased estimator. So an unbiased estimate, so here is sort of an example. So think of a user, and it has sort of many items.
So by ERM according to the zero and loss, not according to the new loss. Because if the new loss function, it can be ERM with respect to the new loss function, right? To the average of precision and recall. Here you probably mean ERM with
No,
respect
but you're
to
going
the
to see you're just seeing one edge every time, right?
You don't see lack of edges?
What?
You don't see lack of edges?
No, you don't see lack of edges, and think of it, you see every user just once.
Okay.
All right. So and you can obtain also unbiased estimators. This is with more caveat. It'll give me a harder time here. So basically, think that I have a user and has a very large subset here. So if I need to compare it, like say a hypothesis that sort of connects X to this item, the red edge or the blue edge, they are very different in the precision. The red edge has a perfect precision because it's inside. The blue edge has a 0 precision. But if n is very large, we are unlikely to be able to differentiate between them. Later, sort of, I will claim that it's not only due to the large degree here, but we can get it also to work with small degrees. Okay, so I'm going to start with the realized setting, and this is sort of where I hope to give you more of an intuition of what's going on. And then later we'll switch to the agnostic setting. So the realized setting is sort of, we have a hypothesis class, and we believe that our target function is in this class. And what we'll show, in fact, the main thing that sort of even prove to you, because they're fairly short, is that if you choose the graph with the maximum likelihood, then you will get what you want. You need, of course, you need to set the sample size correctly, but anyone who knows so sample size, this looks all too familiar. And if you get this sample size, you'll get both low precision and low recall. Okay. So what is maximum likelihood? I'm not going to ask who knows it and who knows, because it's going to embarrass many of people here. So maximum likelihood is sort of a basic statistics, machine learning tool. So it's really, you can think about it sort of, you have a model H, and the likelihood of a model is the conditional probability. It's sort of what's the probability that this model generated the data. Usually I think about it as sort of everything is finite and you have a uniform prior over the models. Right. The maximum likelihood just selects the model which maximizes likelihood. Okay, and this is a pseudo-Bayesian. If you can put a uniform distribution, not always you can put a uniform distribution if the class is continuous, but if you can put a uniform prior, then it's sort of assuming a uniform prior, but it's not assuming a Bayesian model, because it's not assuming that the model was really selected according to this distribution. Okay, so what's going on in our setting? What's the likelihood in our setting? So we are seeing a pairs of xi and vi, right? So the likelihood of a model, sort of first of all, if there is a pair of xi and vi and they are not neighbors, then the likelihood is 0. This model could not have generated the data. And then you are dividing sort of by the neighborhood of the xi's. So this is the likelihood of a model. And like two simple observations is, okay, if vi is not a neighbor of xi, then it's impossible that the model is the correct one under realizability. The complete graph can explain anything, but it will have a low sort of likelihood. This is like, because all this is going to be the number of nodes, this is always going to be 1, so it's like v to the minus m. what would the maximum likelihood do? It will return the model. That sort of, you can think of it of summing up the log of the neighborhoods, assuming that it's not 0. Okay, so this is sort of what I'm advocating, that this is sort of the graph of, if you return this, you, in the realizable case, you will get a good model. 2 slides for a proof sketch. So recall, so if the probability that Vi is not in Xi, under the maximum likelihood, if this probability cannot be 0, right? The recall loss on the training would be 0 here, right? So we know that what we're returning has a 0 recall loss. So the recall there is perfect on the training. So we have a near perfect recall loss in expectation. And you do generalization bound and everything works. The interesting part is the precision. So I try to advocate that the precision, you cannot be an unbiased estimator. So what really is the precision? So the precision is sort of, you sample a user and you sample an item from the user and you're sort of looking now, right, so you're sampling according to the set that you selected, but you're seeing whether it falls inside the target set. Right. So you cannot measure this directly because you don't know those things. Okay, so what can we do? So the main observation in the next slide is going to be that graphs with high precision, right, and low recall is easy to measure. It's 0 on the sample, and it's probably low all over. So those graphs are unlikely to be consistent, and this is why we'll rule them out. Okay, so one slide of, how much time do I have?
10 minutes.
Oh, wow. I can start talk slowly. Well, okay. So so I fix sort of a subset of user, and I have the probability sort of outputting a certain model. So the probability that I output a model it has to be consistent, because otherwise I'm not going to output it. And this is sort of an upper bound on the outputting it. When I'm sort of taking here only the users in which the target sets is much larger than what we proposed. So the main thing that I'm not going to show is that sort of we can relate the empirical precision and the empirical recall. So remember that the empirical recall is going to be very near 0. We are caring about the case that this might be large. So this is going to be related to what we are interested in, sort of like the log of the degrees. So this should be bad. For the bad event, I think of the precision loss is high, the recall is very low. So in such a case, when we look on sort of this upper bound, the probability of outputting it, it's going to be tiny. It's going to be small enough that it's going to be part of our delta. Okay, so I'm done with the realizable case. So bad graphs are unlikely to be consistent. Therefore, what we output is something which is a good graph. Okay. For the agnostic setting. So the agnostic setting, we have 2 results. One is sort of, we can get something to work, but unlike what we love in machine learning, this is not one. Right? This is scales like TCS. We have a constant here. So we can show a constant of 5. And what it really implies is that if you do have a hypothesis with certain precision and recall, we can find out a hypothesis with a very similar recall, but 5 times the precision plus recall that you have. And we can show that it's sort of, you cannot get the 1. So 1.05 should not be taken literally, but should be taken as something strictly bigger than 1. So even if you have just 2 hypotheses, differentiating between them, it would require you to get a constant loss in here. Okay. let me do sort of two summaries. One is sort of a summary of what I presented, and then sort of a very high-level summary of where should I think this be going. So in the realizable setting, we can get both objective, and like very nicely, maximum likelihood, and you can think of it as, we can also do it by minimizing a surrogate loss that I didn't do here. So the realizable case, I think I'm well understanding. In the agnostic case, we understand that you cannot get both. We do have a gap between 1.05 and 5. So 1.05 is almost 1. 5 is a disaster because if you have a mistake of 10%, it will blow it up to 50%, which is nice, constant, but okay. And we do also discuss a semi-realizable case that you have a graph with 0 precision and could have like a recall. Okay, and we can also look on sort of what happens when you have infinite classes, sort of something like the VC dimension or a different combinatorial measure can be applied here. So this is sort of about this work. But trying to frame it in a high level, sort of given all the other talks. So I think sort of my first thing is sort of, I strongly believe that we should look at multi-objectives. And like I was chatting with Tom before, like I never saw a real product that got shipped out because one criteria. You never look at one criteria, right? When you buy a car, you never, like, there's no one number that you decide. You want safety, you want speed, you want comfort, and you want a bunch of, you want a sort of how much the fuel consumption is, how much, right? So usually there's like a whole bunch of things, and trying to linearize them into one number is the wrong thing. So here we took only about 2 objectives, false positive and false negatives, and already sort of things are getting tough. We do have a follow-up work in which we do like an online setting, learning the subset with mistakes bound. And there's like a prior work, and this Aviv was part of, is sort of eliciting using preference from their personal preferences, really understanding the Pareto frontier there and sort of rebuilding it and hashing it away. But in some sense, I think sort of, not all mistakes are created equal, but after I made the slides, I realized that not all the mistakes are created equal, not all correct answers are made equal. Okay, so for show of hands, who here have never had to grade a student paper, exam, or homework? Yeah, I knew it's an unbiased sample of the population, but I'm sure that any one of you who had to grade, okay, if something is completely incorrect, yeah, it's a 0. If something is correct, you give it full credit. There is always like the negotiation of what is a partial credit. But let's even think about the full credit. There is a full credit, which is good, and there's full credit, which is better, and there is a full credit, which is excellent. And somehow, I think sort of in the talks and in the nuances, I think we are sort of missing the fact that something could be correct in different dimensions, and maybe you can even take a few correct answers and make a better correct answer. You can take also a few correct answers and make a worse correct answer because it's going to be lengthy and tiresome. But I think sort of it's something that I'm interested in pursuing. And the other thing is sort of what is acceptable and unacceptable errors, right? Sort of some errors people will accept. Also, if I'll ask you, Durant is an NBA player. In which team did he play the most? Wow. Okay. This what? Okay. This should be sort of sophisticated NBA question. So if I tell you the Golden Gate Warrior, okay. So. She's total loss. So my punchline here was that you shouldn't have answered this question because you should ask me, what is an NBA team? Why is it this? Because an NBA team is not a well-defined thing. We played in two teams which were one team, the Seattle Supersonics and the Oklahoma City Thunders later. They didn't merge. It's a franchise move from Seattle to Oklahoma City and changed names. Is it the same team? Okay. I don't have an answer, but sometimes things are sort of more complex as we see. Okay, let me end here with happy birthday to Avram. So glad to be here. I'm really personally glad to be here because my flights, of course, from Israel got canceled. My United flight got canceled a long time ago, and I was negotiating. I have flights. I have no idea if I can really fly them. So I'm very delighted that I was able to fly and be here with you, Avram. And thank you all for listening.
We have time for a question or two.
Yes, Dan.
Forgive me if you already answered this, but returning to the library idea, do these quantities give us a way of revising our inquiries systematically in order to continually improving results?
So it's more about judging whether a system is giving good results. So you would like them to have high precision and high recall. What we show here is sort of in our model, if you assume that your hypothesis class is rich enough to contain the true model, then doing what any machine learning would call maximum likelihood, lecture number 2 in my class, it's good enough. It's good enough that in the sense if you have enough samples, you will get high precision and high recall. I hope I answered the question.
Well, it's just a question whether it gives us methods of getting better.
I hope that it does, right? So I think for the realizable case, it's more like an analysis. For the agnostic case, it's a different algorithm. Yes, sir.
Another natural algorithm would be to somehow pick the smallest hypothesis that contains the data. And I guess what
This is the maximum likelihood.
it's a little different, right? Because that would be like the sum of the degrees, whereas you're doing sum of the log degrees. Does it matter, or am I thinking?
Thank God that I have co-authors here. Looking at Anne and Lee. We owe you an answer.
I mean, what you were doing makes more sense because in some
Yeah.
sense you would prefer what.
So so it doesn't make sense because I'm sort of worried that there's one user with a huge degree. So you don't want to rule out this entire thing just because of one user. I think this was the logic that you had. Yes?
I have a different question, but if you see all the theoretical or AI models, they run on hardware. So now hardwares are going like in quantum 1 nanometer, 2 nanometer, so they have already leakage and quantum problems and fault tolerance. So how you prefer your theoretical computer science?
How do I fit my model into a quantum computer?
Yeah, not quantum computer, just the chips are going below 1 or 2 nanometers. So do you have any?
Well, because I think it's sort of the fact that we have TPUs and GPUs and this, it really means that we can take a huge amount of data and process it. We do want the processing to be simple on each TPU. And sort of the algorithms here might be sort of simple. But what we are leveraging is really the ability that we have 1 billion users maybe, right? Okay.
All right, let's thank Yishay.
Okay, thank you very much.